Oh, hey guys, what's going on? Means here. It might actually help if I plug in. Give me one moment while I make sure we're not completely boomerang the sound. Should have my thing pop up. Okay, all right, there we go. Let's make sure it's yes, yes. All right. Yeah, all right. It's very awkward when you're looking into the broadcast studio and then you have yourself being rendered over here and yes, yes. Okay. So let me know if it becomes garbly so then I can yell at Apple for fancy over the top headphones that don't like to always sync with their technology and everything. Yes, yes, first world problems. But yes, guys, what's going on? Memes here. And we are back today. I apologize. I think I had like a stomach bug or something for like the past day or two. Oh, my tummy was not happy. I'm not a doctor. Make sure your ground beef is cooked all the way through. I'm just saying. I think that's what it is. Who knows? But all right. So today, what we're going to be talking about, we're going to be talking about charge squared. So as we can see from here before, and I know we have the little light in the way over here. Here's basically big G, the gravitational constant of proportionality. You got your mass one, you got your mass two, you got your R squared over there. Bada boom, bada bing. Inverse square law, blah blah blah. What the heck is that thing? Inverse square just means one. Inverse is basically the opposite. Basically, if you do one over something. You got r squared. It's a radius or a distance squared. All right. That's where you get 1 over r squared. Now, if you notice your little Coulomb constant over there, you got your charge 1, your charge 2, your r squared there. The interesting thing, and we brought this up a little bit the other day, that if you put these in natural units, aka Planck units, so if you get your mass 1 is your Planck mass, your mass 2 is your Planck mass, your radius is the Planck length squared. You throw in the constant of proportionality, big G, you're going to get the Planck force. Basically, the force between those two charges related to that particular distance. Yeah. If you put the Planck charge in for charge 1 and charge 2, you keep the Planck light there, you're going to get the Planck force. Okay. Why am I showing you this? We were talking about this before. What does this have to do with alpha and that whole little thingy and that little thumbnail that I was showing that was going to scare plenty of people away, but that's okay. That's okay. It's the wonderful part about the internet is the best and worst thing is you never know who's watching. For better or worse. Sometimes you just have standard crazy people like me. Occasionally, you have some folks that might be very interesting people that may find this interesting. This is for folks that are looking to learn a little bit more and perhaps notice some things that you don't really hear about. Now, again, maybe these things are very widely known. It's just very often when I'm talking to certain folks that might actually be within physics or mathematics, or some folks that you're like, oh, well, isn't this an obvious thing? Maybe it doesn't really seem that obvious. Um, and again, this is probably just a whole bunch of numerology as I listed in the resources for this video. It's literally just Wolfram Alpha. It's literally me just being a very ADD and occasionally an obsessive individual just grinding away, asking a whole bunch of questions, and occasionally being like, that's absolutely crazy. There's no way that can possibly be true. And you look at it, you're like, well, the things do seem to add up here. I'm going to explain this in a very direct way that, in case somebody that's watching was interested, they should be able to go back and do the exact same things I am. And ultimately, the goal is that somebody can find something so fantastical that it might actually help move humanity forward. Because maybe there's this. I don't want to sound just like a lot of those clickbaity videos, even though yes, there was some clickbait here as I did use here. And this was fake science. To be full disclosure over here with this screenshot. Like over here, I have this 1 over 137. That is not true. That is fake science. It's actually 1 over 137-ish. I apologize. 1 over 1, well, that's 1. Why am I showing you this? Okay. But before we get to that, let's actually say hi to some folks here. We got Jedi Master. Good to see you, my friend. Good to see. Hey, man. It's. I mean, that's one of the great things. Some of the greatest things I hear is when somebody's like, "Oh, I'm trying to learn from you." My big thing is I'm learning from basically everybody because if there's one thing I've learned, it's I don't have the answers, but there's a lot of smart human beings out there. What if I made the crazy assumption that I can learn things from my fellow human beings? I remember that was something that Professor Peterson had said something a long time ago about what if I actually treat other human beings like I could actually learn something from them? I'm like, seems like a pretty good principle. Let's adopt that. Uh, it can be difficult. It can be difficult. It's some folks are easier to listen to than others. I'll be straight up about that. So why am I saying this thing here? Now when you look at this crazy little math thing here, which and again, back in the day, if you were back in like Stephen Wolfram's day of doing particle physics in like the 70s or 80s, what'd you have to do? You'd have to have a journal, or you'd have to have the most recent particle physics database. I actually downloaded one of the like old particle physics databases, and I feel like it was like 18,000 pages long. I might be increasing that by like a tenfold, but I'm pretty sure it was at least like 1,800 pages long. It was like ridiculous. They have all these experiments. You're like, whoa, that's crazy. Modern day, you just go to NIST to get the most recent data or co-data, whatever, whatever government bureau, blah blah blah, you can get, or you just go to Wolfram Alpha that's got at least pretty pretty good alignment with what is currently known here. The benefit too is rather than having to put in like this E squared, that's just the charge of an electron or a proton, because like an electron is negative charge. There's a caveat there because Ben Franklin may have gotten things a little bit reversed. I'm just saying, if you're flying a kite and you got a key on it, get struck by lightning, and you get zapped, that seems like a negative experience to me. So personally, that's my little antidote about why he may have gotten it wrong. I hear it's not supposed to make a difference. Hopefully. Okay. So, but basically, this is the charge of an electron or a proton here. Okay. So rather than having to put like, what is it, like 1.62 times 10 to the minus 19 coulombs or something like that, and having to put on all those things into an actual calculator, do that thing, keep track of all the dimensions, and everything, Wolfram Alpha basically does the hard part for you. Okay. So the whole point of this little thingy here is to show you, because this whole thingy is the definition of alpha, what you may more commonly refer to as the fine structure constant. It's like basically that 1 over 137 ish thingy within physics. Okay. Again, why am I showing this to you? I've done this a bunch of times. It's to show a very interesting thing that not a lot of people, at least, do seem to know. Again, I'm sure there are plenty of folks that know this, but it's occasionally I'll mention this to folks that I've studied physics and stuff. And again, it's such a huge area where it's people very often say, "Oh my God, physics hasn't made progress." It's like, pardon me? If you look at condensed matter physics and stuff, they're doing all these crazy things. The sheer fact we're able to communicate right now is basically a testament to modern scientific technology. Now, if you want to say that the foundations of physics as we know it haven't necessarily been modified or adapted in 100 years, that's fair. As far as I know, the von Neumann axioms and everything for quantum theory are still there. I am going to clip out that little portion about My reaction to Professor Barondus is laying out his flow chart and the general von Neumann axioms. I'm just sitting there listening, and I'm like, crazy. I'm like the only one in the class saying that, and I feel like I mortified a few folks, and then perhaps in some more behind the scenes discussions, even Wolfram may or may not have said a very similar thing. So I don't know. I don't know. Maybe we're just a bunch of loony folks, but I digress. I at least know I am. But okay, the whole thing is you have this thing here. All right. The defined structure constant. It's the reason why it's so amazing is if you take these very important things that pop up all the time in physics, like charge of an electron or proton, like elementary charge unit here. All right. 4 pi, that's a sphere. Oh, okay. I can kind of imagine that. An H bar, that's Planck's reduced constant, the elementary unit of action. C, the maximum of speed in a vacuum that's not technically a vacuum. Speed of light in the vacuum-ish medium. Okay. And then the electric constant. Basically, the magnetic permeability of free space. Is it permeability or permittivity? Hold on. This is always confusing. So, hold on. Wolfram alpha, electric constant. It's going to be permittivity, isn't it? It's the permittivity. All right. The permittivity of free space. I always get those confused. I'm sure I'm the only one. I grind away at this stuff all the time. Welcome, Upcycle. Good to see you. Know we're just going over a very interesting little thing here. So let's actually get to the point here. So the whole interesting thing is if you take all these things together, it gives you a dimensionless number, aka there's no units. So it doesn't come out as a unit of mass, a unit of length, a unit of charge. It's just a dimensionless number that shows the ratio between these different things. Okay. And that's basically about 1 over 137, or this number right here, that was it, not dot 00729, yada, yada, yada. Okay. Now, the interesting thing is, just think about this for a second here. Okay. Now, if you're going to have something with some units and you're going to get something without units, that means you must be dividing a thing with units by the same units. So it's kind of like if you have like just a standard American, you go 10 miles. You go 10 miles and then you divide it by like 2 miles. Miles will cancel out, and then you're just going to get it factor of 5 difference. Right? Because 10 miles divided by 2 miles is just going to be 5. Because the miles will cancel out, and you're just going to have 10 divided by 2 is 5. So if you think about this, you're like, wait a second, this is the dimensionless number. Now, I might not have any dang idea what the heck this bottom number is. But if the top number is charge squared, kind of like the whole title of this video, if the numerator is charge squared and it gives us a dimensionless number with no units, that must mean this bottom thingy, all this jazz, must be in units of charge squared. Hmm. So if you do this one trick, and you take the definition of alpha, the fine structure constant, the constant of proportionality, the reason why electromagnetism is about 1/137th as strong as the strong force. Basically, if you swap out that elementary charge squared and you put in Planck charge squared, it comes out to 1 over 1, which is 1. For those that just want the answer, it's because this whole dang thing is actually the Planck charge squared. But but that's but that's the strength of the strong force, 1. Why Why would the Planck charge put in this come out to be the strong force? Now, simple numerology. It's just a coinkydink. Is it? Now, I don't know this, but I heard fantastical speculation out of, I think it was Dr. Vivian Robertson from the Quacycle Group. God, I need to invite him on before. I was blessed enough to talk with Dr. John Williamson before he passed away, God rest his soul. Um, and it basically, out of the Quacycle Group, Vivian Robinson was somebody that had conjectured that the strong force might just be another expression of electromagnetism. And these graphs and these little charts and everything. And again, it's a very speculative thing, but I look at something like this and it's like, okay, well, this is the charge of an electron or proton. This is literally the maximum of charge, I claim. Um, it's confusing because this is like 10 to the minus 18 coulombs. This is like 10 to the minus 19. They're like, oh, well, that's big. Well, it's negative. So as it gets to negative exponents that are larger, it's technically smaller. But then again, the larger the number it is, actually large. I always get confused. It took me a while to kind of parse through that. But the long story is you're taking this constant of proportionality for electromagnetism. You just swap out one charge or the natural or the limit of charge is the claim, and you get one. So that's an interesting thing. That's not why we're here, though. Why we're here is to explore, because anybody can do this. You can do this here, and that leads to some interesting questions. And I'm sure a bunch of people have answered these questions. But okay, you see this, and you're like, might there be something interesting going on with charge? Okay, so we got all this stuff here. It gives us a dimensionless number. So let's go to our friend Wolfram Alpha here. The that out, and we'll swap up over here. So what might actually be going? You can see, yep, the electric constant is permittivity. Always get those things confused. Okay. So that whole thingy that we hear, so it's like, all right, so fine. Structure, constant. I'll tell you all this thing. So it's basically this whole thingy right here. We got that thingy here. So let's just take that denominator thingy. It's like, all right. So we got 4 pi, speed of light, c, electric constant, E naught, and then h bar, Planck's reduced constant. So we take that whole thing. It gives you this crazy thing here, time squared current. Oh, that doesn't say much to me. So I'm like, all right, those are both squared. Just take the square root. QRT over that little thingy there. Okay, give amperes. Oh, wait, coulombs. It says on mine's 18 coulombs. Oh, that's the Planck electric charge. Oh, okay. Yeah, to all its computable digits according to Wolfram Alpha. Okay, that's Planck charge squared. So let's just do that. Planck charge squared. Now you get this number here. Other interesting things that might go on if we say, I don't know, did something like so that's a natural unit. Let's divide it by, oh, I don't know, another Planck unit. How about the time? Time. In a second. It gives you this number here, 6.525 times 10 to the 7 amperes squared seconds or, or joules per ohm. Don't worry, I don't know what that means either. But the interesting thing is, I do recognize these digits. 6.525. That sounds incredibly familiar. And only just because I've gone down enough Wolfram holes, you right here. Reminds me of a Planck unit, the Planck momentum. 6.25. 6.25. Now the dimensions, we gotta notice the dimensions are completely different. The dimensions and magnitude are completely different. But it's off by 7 orders of magnitude and dimensions. So I'm like, well, if that's the Planck momentum, maybe we could see what the factor that relates them is. Shall we? We shall. So let's just take this whole dang thing, just divide the Planck momentum into it. Let's see what we get. We get precisely 10 to the 7 seconds squared, amperes squared per kilogram meter. Don't worry, I don't know what that is either. What is that? All right. So it's, I believe this is six 150. Okay, 157.9 is, I think that's 16 pi squared. 16 pi squared. Yeah. Long story short is it's 16 pi squared magnetic Coulomb constants. Okay, whatever that might be. Okay. So that's a little hard to parse. Let's look at the other way. Let's just divide that whole thingy into the Planck momentum. This is a little bit more straightforward. Wait a second. That ampere constant we were talking about the other day. It's that thing that seems to be precisely 10 to the minus 7. Ah, that's interesting. But wait a second. Ampere constant, that would mean that we took the Planck charge, we're just dividing it by time, multiplied it by the ampere constant. Oh, we get the Planck momentum. So charge squared divided by time divided by that constant gives us the Planck unit of momentum, which is, that's roughly, what is this? A little over the momentum of a soccer ball going at about 10 meters per second. So you give a soccer ball a good swift kick, that's about 1.5 times that amount of momentum there. Okay. Or about half the impulse of a bat hitting a baseball. About the standard action. If you're a pro ball player, yeah, Big Poppy might hit it a little bit harder than that. But I digress. I'm just some asshole. Okay, well, let's go back. All right. Well, I mean that's kind of interesting. So got the Planck charge. Well, we did time. The next question comes: what happens if you took this charge and you were to divide it by something else? I only get time. Let's do life. What's gonna happen then? Oh, hmm. Here's where things start getting really weird. You get this whole thingy right here. You're like, okay, interpretation, no standard name quantities. The string of digits should mean nothing to you. Okay. The only reason I recognize this string of digits is because I'm like, number one, I'm a crazy person. Number two, gone down enough rabbit holes and have to plug in physically that series of digits eh, to get to other things. Okay, what is this whole thing showing? So, good. Now let's, nope, just divide this whole thing like we did before. Let's just divide it by the Planck mass because that seems to be the digits divided by the, because you trust but verify mass. The Planck mass is basically 2.1764 times 10 to the minus 8 kilograms. Sorry. 2.1764. 2.1764. Again, dimensions are different. Divided by the Planck mass. Let's see what we get. Oh, we get that same thingy there that we had the first time. That means just put this in the numerator. We'll just divide it. Huh. One ampere constant again. Seems to be about precisely 10 to the minus 7. Oh. And this is magnetic permeability. So remember, the electric constant is permeativity. Permeability. Permeability. I always forget. Permeability. The state of quality that a membrane causes it to allow liquid gas to prefer. Okay. Magnetic quantity measuring the influence of a substance on the magnetic flux and regional. All right. Permittivity. Permittivity is defined as the property of a dielectric material that relates the electric to place. Oh, okay, that's a little bit. I just want just the general thing before we even get to the specifics. All right. Material with high permittivity polarizes more in response to an applied electric field. Uh, okay, so that's the other ability for stuff to get in, the ability for the stuff to do things. Okay. That's just my base reaction again. If there's any electrical engineers in the audience, please correct me. So again, this would mean that if you're taking charge square and you're just dividing it by a length, or in this case, the natural unit of length according to the Planck scale. All right. So we just do that ampere constant thingy, 10 to the 7. Okay. That means we just put it, oh wait, multiply it by derp. There we go. All right. So you take those things, you just multiply it by that. Oh, look. Then you're getting the Planck mass right there. All right. This is raising a series of questions. Where do we go next? Oh, hello there, Rick. Good to see a fellow wizard on the internet. But you met Snacks and picked up your new puppet. Oh my God. I've been trying to commission him for a puppet for a while, but then again, he is a pro and I haven't caught up with him in a while. I'm a terrible internet friend. God. Let's see. Okay, Upcycle's saying, wait a second. Let's see. By the way, then Professor Stephen Hawking fixed the constant proportionality at one-fourth, confirming that the entropy of a black hole is proportional to the invariant of its event horizon. That is, I believe, what he had. I literally read that earlier, just because the Wolfram Institute was going over something. It was. It was the offensive name code where it's like it sounds like a curse word or something like that. Long story short, they're talking about data and well, can you go between analog and digital? And some folks believe you can, other folks believe you can't. I have no idea. Actually, if anything, Rick would probably know if that is even feasible there. But long story short, as I looked that up, yes. Yeah, don't mind my terrible. Oh, it auto corrected. There we go. I think it was. Yeah, so was it Bekenstein originally conjectured was log 2 over point 0.8 pi, blah blah blah. Hawking basically adjusted this so it was precisely yes. 1/4. So basically it's just 1/4 is you could pull that four out and just put 1/4 in front of that there. Just the power of kind of algebra right there. Oh, okay. Well, when somebody that is very knowledgeable on something actually gives the actual honest answer of I don't know, that's always interesting. I, I don't know. I'm still scorned from back in high school, and it's like, what's an electron? It's a point particle. Infinitely small. But it exists in all these areas at the same time. I'm like, oh, that's not very sad. Well, it's actually some form of a charge gradient. Well, I'm like, okay, why didn't you say that and stuff? It's like I've watched anime. I've seen enough characters have energy spheres that could have different whirling and crazy things that I could try to start to imagine. It's like I don't know. Uh, where was I? Okay. Yes. So that does appear to be a thing. Interesting. Just because that 1/4 factor, apparently, if you use that crazy little calculation we have where it's like, all right, you take a particle or like an electron, a proton, or a neutron, you take its mass, and then you basically take its classical radius, which is basically if you take its mass times the speed of light and then its classical radius. The classical radius is basically quantifying the mass as electric charge itself. Um, or what it would be is if you were to quantize it as like a sphere of charge. Um, for the electron, normally you just get the natural unit. If you divide it by alpha, I believe you get the Bohr radius. If you multiply it by alpha, the fine structure constant, you get the classical electron radius. Um, there seem to be two radii. That's another question in and of itself. Um, now, and again, I'm sure people have great answers and stuff for that. It's like just an interesting, just something to ponder occasionally. Uh, but for the nucleons or for the baryons, I believe is the technical term for it. Basically, the proton and the neutron. Um, you can get to that factor, or but once you divide by, you basically need a factor of 1/4 there. Why? Dr. Hunziker say at one point, it's like, oh, it's well known that the proton's radius is four times that and stuff. But I'm like, but we've had the proton's mass for a while. And if we had this charge conversion factor, and then when you take that out and you multiply it by 1/4, it literally gets to the more recently recognized. Okay, pause for just one more. Okay, so apparently, about a decade or so ago, we thought the proton's radius was, I think, about 0.87 femtometers. It's like 8.7 times 10 to the minus 16 meters. Ridiculously small thing. There was an experiment, I think, in like 2012 or so, where it's like, it looks like it might actually be less. And it's not like tiny bit less. Right now, it was actually a tiny bit less, but it was about 3% smaller than we believed, which 3% doesn't sound like a huge amount, but if you're dealing with particle physics where we're going out to like so many significant digits, that's a huge amount. Now, my question is if we didn't know that the proton's actual radius, so to speak, or its root mean square charge radius, that's a mouthful, but that's technically what people mean by the proton's radius. And if you watch some more recent videos with Dr. Alexander Unziker on that, he does clarify, and I'm sure nobody sent any emails that may have led to particular videos on this, but I digress. My thing is, if we knew that was a thing, and we had this calculation to quantify like mass as an equivalent charge thing, couldn't we have just predicted this like a while ago? What is it? I think. Oh God, who is it? Nassim or something? Somebody that the Mystify Psi folks had on for a while. I think he had said he had predicted it. I'm not sure if he was doing the same way, but it's just I just go on Wolfram Alpha again. I'm not a good physicist. Don't just set h bar equal to one. Now, if I'm just playing around with some dimensional units, yeah, it's good practice. You can see what's going on. I got things on the board. I can write things down and cancel things out. And it's like, all right, C is equal to the Planck length divided by the Planck time. And then if you want to do C squared, you can square this whole thing. And then if you want to divide, yeah, you could. Not even sure why I started doing that. I'm not even canceling anything out, but it it's the concept of trying to think of the best words for this. I don't want to just say occasionally it's because, number one, I'm not a PhD in physics or mathematics. Full disclosure. I'm going to do it on the internet that maybe the luckiest son of a gun in the world might be something that actually does hold true, but it's more like I'm not a good physicist. I literally just put these things in and just recognize a couple of digits here and there, kind of got a like semi-videographic memory. So it's like I'm pretty good at remembering the first couple of digits and approximate exponential powers to things. And most of the time, it's just a coincidence, just a coincidence. And then you look at things and you're like, well, we only have so much data. You fill it in here. It's, get some new measurements. And it's, okay, well, this seems to extend the prediction. You just follow the scientific method. That's all it is. You see where the observations lead us. That's the thing. Because if there's one thing my old man taught me, God rest his soul, it's truth is the ultimate defense. And that's something that's always stuck with me because it's like if you're wrong, it's all right. You're wrong. You move on. It's fine. Um, and especially you can add an infinite number of epicycles to get whatever solution you want. That's the thing. You can add an epicycle after epicycle after epicycle. Ultimately, it's like at least for me, I'm looking for simplicity because as Vanessa from the monastery said, nature is simple. Now, simplicity for nature might be something that if we were to try to fully compute it ourselves, maybe our heads would explode. Maybe that's far too much information there, but the sheer fact that observers like us seem to be existing, seem to be real, or as Professor Barron does would say, well, if you're, I think, an anti-realist or something like that, well, that person doesn't exist anyway, so we don't have to deal with them. Uh, I realized I was kind of cruel and again, I don't know enough about all that realism and stuff like that. It's like, oh, I seem to be here, so I might as well kind of act like stuff is going on. Oh, yeah. That's a great question. I don't know. Every once in a while, cycles point out that 1/4 thingy that had popped up in yeah those other calculations. I don't know. Who knows? Maybe Stephen Wolfram was right. Maybe just electrons, protons, and stuff. Maybe they're just other expressions of black holes or something like that. Who knows? Maybe it's black hole turtles all the way down. I don't know. Shadow turtles, whatever. I don't know. Oh, it sounds like a new Teenage Mutant Ninja Turtles. God, secrets of the Dark Turtles. Turtle power. I think I have a meme for this somewhere. Okay, maybe not fully appropriate, but here we go.
It's turtles all the way down.
simplify it. Such a pain in the butt. Can't bring me anywhere. All right, so where the heck were we? Okay, so we had gone. Yes, back to a point. So that whole charge thingy, and again, noticing things. All right. The only way I might be able to actually notice things is again, as I was saying, I'm pretty good at remembering a couple of things. And again, this wouldn't mean anything. Like if I need to go through all the effort, like smart people far smarter than me 100 years ago were setting up all these things where it's like, all right, you need to find the most recent things. And we only had like three, four, five significant digits or so, maybe six or seven, seven-ish for electromagnetism, because that's when things started to have to get quantum because things started getting weird around the seventh significant decimal place. Um, maybe, maybe there's something going on there. Now, again, if I need to go through and find this information, do all the honestly, I don't think I would have the patience to do any of this. I just happen to be alive with interest and have been guided by a lot of really smart folks around me, providing additional guidance and insight about where to look. So, as just simple monkey with a magic typewriter and an idea of where to look, I can ask a ridiculous amount of questions to Wolfram Alpha that I don't know, basically has the knowledge, the sum total knowledge of so much of physics, so to speak, already preloaded there for me. So I can look at all these relations and heck, I don't even need to ask the questions. I can just be like, all right, how about this? It's mass. Oh, here we go. Mass of Earth. The mass of Earth is like 10 to the 24 kilograms or something. Okay, so about 6 times 10 to the two. I'm sorry, I only know that just because I had looked it up the other day. So it's like, all right, you get the mass of Earth. It's showing you how much in pounds it would be, how much in grams, metric tons, solar masses, relationships to Jupiter, about 18 Mercuries in mass. The total mass energy, if you were to convert all the mass of Earth into energy, it's going to be like 10 to the 41 joules, 10 to the 60, like it tells me the relationships. You just ask the question, and it shows you questions that I would have had no idea of what it is. And it's like, all right, you got a guy like Fab that comes along, and it's like, oh, I was able to calculate a bunch of these things using Wolfram Alpha. This seems to be a very powerful tool. I would highly recommend people using it. And, okay, I hear that. I'm like, all right. I start playing around, and I hear Stephen Wolfram. He's like, the Wolfram language is like a superpower. More people should use it. I'm like, well, here's the thing. Whatever you might think of Thad or Stephen Wolfram, for better or worse, it's like when you start hearing two folks saying very similar things, and they seem to have done a whole bunch of interesting things, and perhaps solved and or at least provided the beginnings of conversations about what actually might be going on. It's like, all right, look where people intersect on things. And then even a lot of folks just within physics itself. And again, whatever you think of Stephen Wolfram's physics project and stuff like that, it's like, for me, it's like mod. Like string theory. String theory is a model. I mean, people will like say all these things, oh, this, that, the other thing. It's like, well, it's a model. You're using a model to try to model what's going on in reality. It's the whole be wary of confusing the map with the territory itself. Now, might the map actually be the territory? If you were to get everything right, maybe. I don't have the answer to that. Can't say. Again, I'm looking for a map. If anybody's got some good pieces of the map, feel free to send them my way. But it's just that you have a tool here and it says these things. And if you can start to recognize interesting things, maybe interesting things are gonna come around there. It's so that's why I just when I start relating these different things, it's like, all right, well, this is interesting. I get charge square because what is charge? Anastasia from the Mystified Side podcast, she was asking that in college. It's like she was in biology, and it's like, yeah, it's like, well, you got all these things here. It's a factor charge. And she's like, what is charge? And our professor would be like, well, we'll talk to these people. And goes over to those other folks. It's like, well, what is charge? It's like, well, go to the, or it's like, well, here's some equations. It's like, okay, that's cool, but what is going on? She never got a satisfactory answer. Yeah, I don't know. Maybe it's just I sympathize because one of the first things I ever asked Thad when I went gone out to the Physics Monastery, I just went out there and he's like, "Hey, you want to come up and say some words?" I'm like, "I'm just a dude. What are you doing?" It's like you want me to come up here, stand up here for a video, and try to say something intelligent? I don't know what's going on, but hey, it, that's why I appreciate a lot of what Thad's done for like mentoring me and stuff like that. He's like, "Hey, man, it's why not? If you're interested in this stuff, do it." So, um, yeah, no, no, I will always appreciate that. Thank you. But it's one of those things where it's like, if somebody shows you that something that, and again, these are claims, and again, we're gonna have these things evaluated. But if you see somebody that has done something that a lot of other folks say cannot be done, they have literally done the impossible. Well, I did learn from Professor Brian Keating that of Arthur Clarke's laws that the only way to see what is possible is to venture even further beyond into the impossible. Well, that's where we got the name for the Into the Impossible podcast and stuff. So I'm like, all right, that sounds pretty cool. So I'm like, okay, when you see somebody that does that, and then occasionally, due to a sheer circumstance of luck, you may come across the occasional other individual that seemingly has done the impossible as well. Things that people say that cannot be done, and you're like, all right, well, maybe these things are not impossible. Maybe they're just really hard. And occasionally, are these things hard because they are truly hard, or it's just the way things have been framed in our mind? Because a lot of times it's like we're coming from a particular way, and we have this. Yeah, I don't want to say inherent bias, but I can't think of anything different than just it's our standard inherent bias and stuff like. Because if you're always taught that, well, this is the way it is, and someone's like, no, it's just completely this other way. It's like blasphemy. They're obviously a witch. As somebody that lived in the Commonwealth, where yeah, in our history, we literally burn folks upon accusations of being witches. Yeah, something about that history in me is like, yeah, maybe we should be wary about burning of witches and the digging of ditches, yada yada yada. Regular. Stuff. But okay, I'm sorry. I've been ranting like crazy. Oh, no worries, no worries. Well, that's the thing, Poindexter. It's like I remember, what was it? Even with Steve. Hold on, I need to show this clip because this is fascinating, and this is pretty telling. Because a lot of times people like what is actually going on, what is happening with different things. Like, all right, so Wolfram Alpha, Ethan. All right, Wolfram Alpha surprises Stephen Wolfram. This was fun, and I managed to get a good screenshot just because it's I don't know. Sometimes it's It's good to see when people are smiling. So let me actually. God, silly face. There we go. Oh, all right, all right. No, 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 no. Thank you, Rick. Oh God, good catch. I was doing the window there. All right, sorry. Boomer. Try this one more time.
But it's very important that you have a very solid foundation because if not, you build that tower up and it's probably going to fall down. And to just give the folks a quick list of what goes through my mind when you talk about the Wolfram language and technology, and just go to Wolfram Alpha, just a website that's free. I type in speed, just gives us the physical quality, common symbols, length divided by time, meters per second. And the very interesting thing here, when we start talking about potential faster than speed of light travel, I noticed, and this was something that I don't hear many folks talk about, on Wolfram Alpha, the lower limit on the speed of quantum information is 1.6 times 10 to the 13 meters per second. The speed of light is approximately 2.998 times 10 to the 8 meters per second. And this has been on Wolfram Alpha for a while, and
That's
I,
interesting.
I just think it's pretty neat. I think it's pretty well. Wasn't this proven recently with the entanglement experiment last year? Won the I believe the Nobel Prize in physics, showing that information per se is not necessarily localized. I mean, that's fascinating.
Right, right. That's cool. Actually, I should. You see, this is one of the things that this is one of the facts about creating technology and so on, and particularly creating sort of open-ended technology. One has no idea what one's technology is going to do or be capable of, and I think it's a good example. Thank you.
Okay. The other thing that gets me a little bit about that was just I remember showing showing him that, and then I think it was about a year or so later where I think he was having a conversation, I think at one of the summer schools from a year or so ago with Jonathan Garrod, and I think Jonathan Garrod, I think that was the lower limit on the speed of theoretical speed of quantum information, and then I think Jonathan Garrod was, I think, quoting the upper limit of quantum information. And I think I saw maybe just a little look in his eye about, okay, I remember hearing something about this before. So it's just interesting when you learn something and when somebody brings it up and you're like, I remember I had a conversation with somebody. It's like, what was it? At one point, there was, we were at the monastery and Echelon was telling a story about how somebody was showing him something or they were going over how to do something in some particular language like seemed very obscure that he knew like nothing about or something, and then somebody asked him like the next day or so, it's like, could you help us with something about this? And he's like, well, I really don't know anything about that. But the thing that they asked him was the one thing that he had actually done before. And they're like, wow, you're really good at this. It's like, no, no, that was literally the one thing that I knew how to do within that parameterization of the language. I had a similar thing where was it because on one of the old Eric Weinstein discords and stuff before people there kind of drove Eric from that part of the internet was um was it, somebody was talking about something about like philosophy or something. I gave like some answer or something, and they're like something about Quine's two dogmas or something about perspectives and something. And I gave get something that seemed kind of like an eloquent, fancy answer or something, and somebody's like, "Oh, you must spend a lot of time reading all of these great authors and everything like that." It's like, no, I was just helping one of my friends with her like psychology homework or sociology homework or something like that, and the assignment was to watch The Expanse and then read like Quine's Two Dogmas. I'm terrible at reading things that I'm not really super into. So I'm like, all right, so rather than reading the whole 60 whatever pages of Quine's Two Dogmas, well, here's like a 40 or 50-minute video of Quine himself explaining his two dogmas. Cool. So we just listen to that and asking some questions. We're going through the philosophical exercise and everything, and hey, she ended up getting an A. So it's like, no, 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 I'm not an expert on any of those fancy things. That was like the one thing that I literally just did last night. So occasionally, occasionally those things happen. I think they call that, what is it, synchronicity. It's fortuitous things aligning there. And and you sit back and like, I think a lot of us have had some of those situations where you're like, the chances of that happening in that particular way are so astronomically improbable. You're like, I think that's the definition of a miracle. Now, hey, listen, hey, I ain't nobody's boss. You go your way, I'll go Yahweh. I don't really care. I'm sure that's my big thing. It's all right, where are we? Oh, the other thing is, um, when you hear, where is it? We'll give Richard Feynman's most fantastic moment. Because you'll hear these things. Sorry, Richard Feynman. So, just bring it up here. Uh, okay, so, okay, this is fascinating. This is from this is Richard Feynman's lecture, Los Alamos from Below. This is apparently the Quagmire Trail. So when you listen through this, you realize some of the synchronicity and the things that could go on. Just listen to what the Professor Feynman says here.
Room in a big lot, but it was the same room on the other side, and things like that. So if you have too much stuff together, it goes up, you see. So it was I went through the entire plant, and I have a very bad memory, but when I work intensively, I have a good short-term memory. And so I could remember all kinds of crazy things like building 9207, VAT number, so-and-so, and so forth, you see. So I had all that stuff. I went home that night, and I went through the whole thing, explaining where all the dangers were, what you would have to do to fix. It's rather easy. You put cadmium in solutions to absorb the neutrons in the water. You separate the boxes so they're not too dense, too much uranium together, and so on, according to certain rules. And so I worked out all the examples and how it worked. I felt that you couldn't make the plant safe unless you knew how it worked and so forth. So the next day there's going to be a big meeting. Well, I forgot to say before I left, Oppenheimer said to me, now he said, when you go, their following people are technically able.
Okay, so just for reference, Oppenheimer, yes, that Oppenheimer, yes, the guy with the hat, the the, the guy that will help set up the prequel for the Godzilla movies. Uh, Basically, Oppenheimer, one of the most notable and kind of powerful organizing scientists of the time, young Dick Feynman, hasn't finished his PhD. Literally, still a student. Little Richard Feynman. Okay, he's getting he's getting the word from the big man. Uh, Okay. So just putting that in reference here.
People down there at Oak Ridge, Mr. Julian Webb, so and so and so. I want you to make sure that these people are at the meeting, that you tell them the safety problem, that they really understand they're in charge of it. And I said, suppose they're not at the meeting, what am I supposed to do? He said, then you should say, Los Alamos cannot accept the responsibility for the safety of the Oak Ridge plant unless these guys. I said, you mean me, Little Richard's going to go in there and say? He says, yes, Little Richard, you go and do that. I said, I really grew up fast. You know what I mean? So when I arrived, sure enough, I arrived there, and the meeting was the next day, and all these people from the company, the big shots in the company, and the technical people that I wanted were there, and the generals and so forth that were interested in the problems and organizing everything. It was a big meeting about this very serious problem of the safety, because the plant would never work. It would have blown up. I swear it would have, if nobody had paid attention to it. So there was a lieutenant who took care of me. He told me that some colonel says that I shouldn't tell him how the neutrons work and all the details, because we want to keep the thing separate. I just tell him what to do to keep it safe. I said, in my opinion, it's impossible for them to understand or to obey a bunch of rules that they don't understand unless they understand how it works. And so it's my opinion that it's only going to work if I tell them. And Los Alamos cannot accept the responsibility for the safety of the Oak Ridge plant unless they are fully informed as to how it works. It was great.
Just literally repeated Oppenheimer's words about. Now you can argue about that, but I think the general principle of if you tell people to do a bunch of things and they have no idea why they're doing it, people might kind of occasionally slack. It's not like we've had anything like that in recent history. That yeah, I digress. So it continues on.
So he goes to the colonel, and he says to the colonel, so this is just 5 minutes, he says. So he goes to the window, and he starts and thinks. And that's what they're very good at.
And I find the blueprint. Okay. This is Richard Feynman, I believe, his greatest moment.
How do you look at a plant that ain't built yet? I don't know. So I go into this room with these fellas, take me into the room. There was always a Lieutenant Zumwalt that was always coming around with me, taking care of me. You know, I had to have an escort everywhere.
It's a handler, yeah.
So he goes with me, takes me into this room, and there are these two engineers and a long table, great big long table, tremendous thing, covered with a blueprint that's as big as a table. Not one blueprint, but a stack of blueprints like this. I took mechanical drawing when I was in school, but I wasn't too good at reading blueprints. So they start to explain.
Note, again, young Richard Feynman been going through the plant. At one point, what he did is like evaporator 24 in room 1947 or something like that. It's like he just remembered the short little name about one very specific thing. People are like, oh my God, he must know the whole plant. It's like, no, that's literally the only part that he had like memorized there. The general idea, but that's the one very specific thing. But being able to rename that one very specific part kind of gives you the air of, oh, this person must be a professional because you remembered that one thing. Yeah, a young guy that you're like, all right, all these military folks, all these smart folks, I'm just a young dude without even having like my degree yet. It's like, so he was trying to get an air of, I know what I'm talking about. Okay. So now he's supposed to inspect the plant that they have yet to build, and they have all these blueprints. They're laying them out, and they start to explain it to him.
Me because they thought I was a genius. And they start out, Mr. Piper, we'd like you to understand, the plant is so designed. You see, one of the things we had to avoid was accumulation. Problems like there's an evaporator working, which is trying to accumulate the stuff. If the valve gets stuck or something like that and accumulate too much stuff, it'll explode. So they explained to me that this plant is designed so that no one valve, if any one valve gets stuck, nothing will happen. It needs at least two valves everywhere. Okay. So then he's explaining how it works.
So just say, everything should be fine. Mr. Feynman, everything is totally fine. We're going to explain how this all works. It's elementary, my dear Feynman. Because I think he's a genius from him basically seeming to be so smart while he was there. So this is how they start explaining to him in the words of Dick Feynman. This is, oh, God.
The carbon tetrachloride comes in here, the uranium nitrate from here comes in here, it goes up and down, it goes through the floor, comes up through the pipes, coming up from the second floor, through the blueprints, down, up, down, up. Very fast talking, explaining it. Very complicated chemical plant. I'm completely dazed. Worse. I don't know what the symbols on the blueprint mean. There's some kind of a thing that at first I think it's a window. It's a square with a little cross in the middle like this, all over the damn place. Lines with this damn square, lines with this damn square. I think it's a window. No, it can't be a window because it ain't always at the edge. I want to ask him what it is. Now, you must have been in a situation like this. You didn't ask him right away. Right away, it would have been okay. But they've been talking a little bit too long.
Haven't we all been there where it's like something gets said? It's like, I should say something. You did not say something. You waited a wee bit too long. Now it's like, why didn't you say anything before? We've been rambling on all this time. So, in the air of synchronicity, this is what I think might be one of the greatest things ever.
You hesitated too long. If you ask them now, they'll say, what are you wasting my time all this time for? I don't know what to do. I think to myself, I swear, often in my life I've been lucky. You are not going to believe this story, but I swear it's absolutely true. It's such sensational luck. What am I going to do? What am I going to do? I got an idea. Maybe it's a valve. So in order to find out whether it's a valve or not, I take my finger and I put it down in the middle of one of the blueprints on page number 3 down in here, and I say, what happens if this valve gets stuck? Figuring they're going to say, that's not a valve, so that's a window. So one looks at the other and says, well, if that valve gets stuck, and they go up and down in the blueprints, up and down the blueprints, or they go up and down the blueprints, back and forth, and back and forth, and back and forth, they both look at each other and they chick, 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 and they turn around to me and they open them out like this. You're absolutely right, sir. So, they roll up the blueprints and away they went, and we...
Okay, so that initially, my initial response to that is either that is literally the biggest piece of luck of just pointing in the one fatal flaw in the plant, or maybe they looked at it and they're like, we're just going to assume he's right because he's obviously a genius. Could just be synchronicity where it's like, well, maybe, oh, there's a whole bunch of things going in there and there. It's like, well, that kind of seems to be in the center. Maybe that's some good intuition or just sheer luck. It's like, what happened to this?
We walked out.
And the
Mr.
response
Zumwalt,
here.
who'd been following me all the way through, he says, you're a genius. He says, I got the idea you're a genius when you went through the plant once and you could tell them about evaporator C21 in building 9207 the next morning. He says, and when you knew all about the neutrons, you were a genius. But what you have just done, he said, was so fantastic. I want to know how. How do you do something like that? I told him, you try to find out whether it's a valve or not.
Ladies and gentlemen, Professor Dick Feynman. So, here's the thing, Poindexter. When I first heard that lecture, that was one of the first lectures that I heard of Dick Feynman. That was like when you listen to that beginning thing and he starts coming out, it literally does sound like stand up. I was just like, is this what Roger Williams would have been like if he became a physicist? Like that. That was literally what I thought, and that's why at one point I asked Stephen Wolfram, like, if physics hadn't worked out for him, could he have made it as a stand-up comedian? And he gave his thoughts. He's like, yeah, probably not good stand-up comedian, but good expositor of science. Rick is commenting, to see the whole plant in a single valve is the same as to see the universe in a grain of sand. Oh, I like that quote. I like that. Well, I was it's that's very much like William Blake. See the world in a grain of sand, heaven in a white flower. Hold infinity in the palm of your hand, and eternity in an hour. Also from Ultraman. Ultraman Towards the Future. That one. Do I have? I don't have that one, do I? Oh, I got that in a bunch of other things, don't I? Dun, dun, dun. Did we have that? No, no. We just have the follow-up to see the world in the grain of sand, which is General Brewer going.
You finally flipped.
We flipped. Yes, yes. No, it's a powerful one. Where were we? Oh, I should probably actually finish off the little interesting thingy that I said we were going to go through. Let's back the charge squared. All right. So apparently, what have we deduced, surmised? So basically, it's all right. Charge squared, and we divide by time. Put in that amper constant of magnetic permeability. Oh, we get Planck momentum. All right, so we get momentum there. All right. We get charge squared divide by length. We put that, and we do that amper constant. Okay, so we go from momentum, go to mass. Okay, so all we've literally done here, we went from length, time to length. We got momentum, we got mass. So that of course leads to the next question, which is what happens if we put mass there? I mean, maybe this shouldn't be that all surprising. It's okay. Full disclosure. I noticed something like this. I think about like a year or so ago, but I did not have enough experience to really just say. I'm just like, why do these digits seem to pop up in weird ways? And it was very ad hoc. It's like I'm discovering all these things, and I don't know why these are things or any of these things are here. And then it's like, all right, as things became more coherent and start working with the units and everything, just kind of seeing how things kind of wedge or fit together there, and you just start seeing the pattern, so to speak. And again, it's kind of a noobish pattern, but it's I love building with Legos, Lincoln Logs, and I don't care what it is. Fundamental units or something. If these things seem to go together in very interesting ways that can tell us about what might be going on within our reality, well, maybe that's something that's worth paying attention to. So, where were we? Let's go back. How the heck we get? Let's pull off the amper curve. Let's go right here. Planck charge squared divided by the Planck mass. What's that give us? Now, again, when you start, if you've done enough calculations with these things, when you start seeing that 1.616, it's like, all right, those are the beginning digits to the Planck length. But again, if you've seen it enough, people might be like, I could never memorize that. It's like, yeah, but it's not like any kids that ever memorize a whole bunch of baseball stats for like some of their favorite ball players. Oh, that's different. Why? Because I'm interested in that. That's the thing. It's interest. If you are interested in something, you can help figure out what's going on, or at least I claim you're going to have a much higher chance of figuring out what's going on because you're actually interested in something. If you're not interested in something, yeah, maybe you can figure something out. Maybe you're just a complete and utter genius and you can figure out all these things that you don't even care about. Okay. I ain't no Einstein. I'm literally a dude. It's got some interest that has computational technology that gives me like magnitude superpowers of information that a lot of people far smarter than me did not have access to. I'm just choosing to use it, assuming that maybe there's some there. It also doesn't hurt to have a couple of folks that have seemingly done the impossible using similar tools. Um, Also, along with the ability to think in an uninterrupted fashion, having time to think things through on an extremely deep level. And if you also have the ability to mathematically represent things, probably doesn't hurt either. If you can actually express something in a way where you can put together in some equation or some relationship between the fundamental stuff of reality, being able to describe the things that we observe and experience within our realm. You can do that, isn't that the goal? We're trying to figure out what's going on. Yes, a short ploy on, hey guys, what's going on? I don't know. Who knows? All right. Long story short is if you notice this here, this is kind of the dead giveaway. You see these digits. You see this power. Okay. These are the digits of the Planck line. This is 10 to the negative 28. Now, the Planck length is of magnitude 10 to the minus 35. So that means, wait a second, these digits are 7 orders of magnitude off. And, oh, these are the wrong dimensions. So what could shift this by 7 orders of magnitude and get us to the right dimension? You got it. Amper's constant, which gives us the Planck length there. Very neat. Very neat. Now, you might ask what happens is, oh, I say there's like 5 dimensions, like that has been said. Well, next, the next dimension is charge. So if you were to just take charge there, just going to give you, it's just going to give you a Planck charge to the first because, well, yeah. Now, and you could do temperature, but the problem is with temperature, it doesn't really do anything until you express it in energy. And then if you just do energy, you start getting capacitive load and everything. And yeah, this is basically where the end of my knowledge basically comes from. So, and again, group velocity dispersion rates. Like I mean, I don't really know what this stuff is. I think this is like cosmological physics and stuff like that. Well, that's interesting. That is about the magnitude of the cosmological constant-ish. Huh. Okay. I mean, the other things are much more direct forward. These things I don't spend enough time on. I'm very ADD with some things. I really get obsessive with certain things and just like looking into them. I'm terrible at fully composing these things. Like I'll half write papers, and once I get the general thing, I go into something new and shiny, and I'm just like, I really need to focus on one, finishing things. Finishing things because I've got at least enough ideas that I do need to formally submit. And some of these things, I either have papers or papers that are mostly done, where if I just need like a data analysis, because I know I have places where I can actually submit them now. And I've been saying that since last year, and I just need to make it so. Uh, Planck mass, Planck length equals Planck's. Let's see. Planck mass, length. Gonna be mass distance like 10 to the 35 units. No, 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 no. 10 to the minus 43 mass distance. And then I charge squared. Like charge squared, and then by Planck charge squared divided by Ampere's constant. Planck charge times Ampere's constant gives mass distance. Huh. So, okay, so it's Planck charge times Planck charge times Ampere's constant is mass distance. Huh, that's interesting. I agree. That is very cool. It's well that was just one of those things because it's uh, what somebody had spurred it. I think maybe it was at the end of one of these streams or something the other day. Or very often somebody will say something. It's like I don't know, I ask a little question, or somebody will just mention something in a video. They will do a quick calculation. It's like, well, seeing as I am sorely lacking in actual like physics and mathematics and stuff like that, somebody says something and I can quickly ask them questions. I can at least practice it. It's one of the things that Dick Feynman had said at one point was, um, do all the calculations that are out there. It's um, I don't think maybe he meant it literally. I take it more of just as an adage of calculate everything that has already been calculated, where it's like do everything, but at least going through the exercise of being like, all right, well, this is this. What would happen if this was the case? And at least going through and seeing if this is true, why might this be the case? So, I mean, that might be a very interesting thing. Uh, we just found Planck mass, Planck length equals, yeah, that's, oh, the reason why that needs to be the case. Okay, okay. I know why. I know why. I know why. Because if we take this thingy here and we divide it by the like charge squared. Okay, it's doing those force. Okay. Oh yeah, those force meters and everything. That's just something that relates to Earth, and that's it's a well-known thing. And basically, it is set to the gravitational average constant of Earth. So it's like that thing that blew my mind. I'm just like, wait, wait. I did go further there, just uh, kg force meters. Okay, gravitational field. Yeah. Okay. So I was just like, wait, what the heck is going on? But kilogram meters. The reason why is because at least for Thad's little inversion box, the claim is the ampere is something weird is going on, and that's why he basically utilized the binomial theorem to basically be like, all right, we have this piece here, generally referred to as the outer action, and then some inner action or some second component there basically ends up having that as a dimensionless deviation there. Because basically, if you just do, it's the whole thing was he taught me was the Planck mass, Planck length over the Planck charge squared. So this is mass distance divided by charge squared gives us Ampere's constant. Okay. So I'm like, th- okay, this is actually almost I feel like a circuit in my brain is actually just been connected. Like I feel like there was an anode where I just kind of had like I knew this was a thing, and then until we actually went around it, going and calculating it from this side. Now I feel like it's actually connected because I could be like, oh, Thad's been talking about this for a while. So, uh, yes. Okay. So I mean, that literally is the definition of Ampere's constant. So it's like if we take that and then we divide this by the Planck charge, we should get, yeah. Uh, Actually, what happens when we just, okay, if we do it by Planck charge squared? All right. No, we need to multiply. Well, then we're going to get mass distance. And then divide. Okay. So we have that. I mean, I just really find it fascinating that it's like you have a Planck unit, you have these other Planck units, and you're literally getting out the same digits, and it's just off by 10 to the minus 7. I mean, that seems extraordinarily convenient. Um, Now, potentially, again, hypothetically, if it wasn't precisely 10 to the minus 7, something like, oh, I don't know, like 10 to the minus 8 or like 9.9992999 times 10 to the negative 8. Maybe there's just a wee bit of a difference there or something like that. I'm just saying if there was a slight deviation from 10 to the minus 7, might that have a little bit of a ripple effect on some of the other things we're calculating if we're going to like 10, 12, 14 significant digits? Just a potential thought there. Um, cool. All right. I feel like I kind of maybe connected something in my head there. Distance. Frankly, this was only one picture. I'm not really sure what that. Well, it's just interesting that it's charged square because when you start playing around with some of these other things, like, is it, I don't think I've seen this for some other ones. All right. Maybe it's just me. Yeah, group recession velocity thingy. Length. It doesn't seem to be. Charge is the one thing that does really seem to line up. And then again, if it's going to be a 10 to the negative 7 factor, it's like whatever digits you have there, that's a very interesting thing. And again, the claim that that is proposed is something very interesting seems to be happening around about the seventh digit of magnitude within our current SI system. Maybe there's nothing at all going there. Maybe all of us were just barking up the wrong tree, but just occasionally, and again, it's circumstantial, but when you start seeing charge squared, and it seems to be kicking out different things, and occasionally, when you do different, there are some crazy calculations that I really haven't, I don't think I've gone over publicly yet, that you start looking at different relationships between things, and all of a sudden you're like, when you see digits of those Planck units, and like you see, occasionally you might see a couple, you know, two or three. And once you start seeing four or five, you're like, that seems to be the basis of our knowledge, and it seems to be matching pretty dang well I don't see any reason this should be here at all. Why? These are just the things that make me go, hmm. But like mass, like mass, clank. Those H bar divide by. Oh, no, no, no. I can do this in my head. I can do. No, I'm going to do this on the board. Hold on. Let me do this. Let me do this. I can do this one. See, I swear I've learned something. All right. So Rick is saying, so Planck mass, Planck length. All right. We got Planck times the length Planck. I'm going to set that equal to H bar C. All right. I'm going to do blah, blah, blah. H bar is it's mass area, so it's length squared, right? So it's time there. The P. We're going to divide this by C, which is length, divide by time. All right, so cancel that out, cancel that out, cancel that out, cancel that out. Yes, that is correct. Planck mass times Planck length is the elementary unit of action divided by the speed of light. I feel like I should have spent more time looking at this number and everything, just because that's popped up before, and I made some atrocious claims with that before, and it was just a massive error on my part, so that's why I kind of got away from that. I'm just kind of purged it from my mind a little bit. And then H bar divided by C equals length times length. Hey, H bar C equals like mass length equals ampere constant charge squared. Constant. I don't think it liked all those equalities. Let's just do one. Uh, Oh, sure. It helps when you set it up correctly. Yes, all right. That equals true. And then maybe we'll actually let's think pull that out. This should be. That's what we just said. Okay, so yep, that is true. Yep. So yeah, h bar divided by c is Planck mass times Planck length equals Ampere's constant times Planck charge squared. Ooh, that's. I, I need to finish up the things that are currently on my burner that have either overboiled, overcooked, or something. Put those together, and then my next project needs to be just diagramming all these dang units in a way that people can easily traverse and just, I don't know, do. If they have video games and skill trees where you can link through and easily do that, I should be able to do this in some little 3D landscape that should be able to be navigated there. Because one, I think it's like the ultimate crazy, quote unquote, crazy person way of diagramming all these things. But I'm like, well, if this is reality as we've defined it, it's going to be some crazy spider web of things. Okay, maybe. Maybe it'll tell us something interesting. Maybe there's going to be some pattern that we just sit back and we're like, oh my God, that should have been obvious the whole time. Uh, I'm hoping that we're gonna find that, but that's all I really got. Just kind of wanted to go over that whole what's going on with charge squared. Why does it seem to be able to tell a lot, and we even really know what the heck charge is? Seems to be maybe one of those questions that maybe we'll find out sooner rather than later. Maybe it will always be a mystery. Maybe it's computationally irreducible, but who knows? I'm pretty sure we could find some computational reducibility in what's going on. Yeah, because we can. It's important for moving humanity forward. Why? That's what science is supposed to do, right? That's all I really got for now. So, good to be back, and we'll be talking about some other interesting stuff and things going on, like tomorrow. So, until then, take care of yourselves. Peace out, everybody. It's a wacky and wild world out there, but hey, it's hoping for a better tomorrow. Starts one person, conversation at a time. Peace out, everybody.